Welcome back, class. Yeah, I have a pretty tricky example problem for you guys now from chapter 6 here to talk about or to observe, I guess, application of Newton's laws to objects where we have not only different types of forces, tension, gravity, and so on, but we also have frictional force. So this is the problem here, and it's a pretty tricky one. And in fact, there's actually two different ways you can go about solving this problem. And in the solutions here in a minute, I'm going to show you both of them. But I want you to start by trying to figure this one out on your own. So let's imagine you have these three blocks here. Block A is 12 kilograms, block B is 7 kilograms, and block C is 10 kilograms in mass. You have them set up exactly as you see here, and we know that there's a kinetic force of friction, a kinetic coefficient of friction between block B and the table of 0.1. All right? Again, there's no units on coefficients of friction. So 0.1. I'm going to go ahead and give you the hint that when you release this system, it's going to have a net force in one direction, so it will accelerate. All right? So I'm asking you to determine what is the magnitude and direction of that acceleration. So based on just that information given to you, I want you to solve for the acceleration of this system. So notice block A and B are tied together via this string, and we're going to say it's a massless string over a frictionless pulley, and block B and C are attached together via this string, again over a frictionless pulley and with a massless string. Now keep in mind these are two different strings, so they're going to have two different tensions in them. Pause the video and try to solve. Ready? Go. All right, so as I mentioned at the beginning of this problem, there's two ways to solve this problem. And those two ways are, first of all, you can either choose to take each block and deal with those blocks individually, all right? Or you can take the entire system as a whole and deal with the system as a whole as well. I'm going to introduce to you how to do both of these and solve the problem thoroughly using the simpler of the two. So if you deal with the system as a whole, you're going to look at all of the blocks together as one piece. You're going to say, okay, I have these three blocks that are all moving together. And you may or may not know the direction it's going to move straight away. In this case, you should be able to already determine which way it's going to move. But if you don't, that's okay. You just pick a direction. But I'm going to choose and say, well, since block A is more massive than block C, I think this whole system is going to move in a counterclockwise manner. So everything's going to accelerate in this direction. So block A will accelerate down, block B to the left, and block C up. So that's how you would deal with the system as a whole, and then you do some of the forces on the system as a whole in that direction. But some people find the system as a whole method a bit confusing. So your alternative is to deal with the system by breaking it up individually, looking at each block. So you could say, okay, I got block A, block B, and block C, and you can do some of the forces for each block individually and start to solve. Both ways are perfectly accurate and both ways work well. But I just want to briefly show you how to do each of these two in order to help you better solve this problem and future problems. So let's start with the individual block method. This is a method that's always going to work every time. So if you're confused by the system as a whole, ignore it and just do things individually. So what we're going to do is we're going to isolate each mass, each of our objects, and do some of the forces for each of those. But before we do, as we know, for the problem-solving steps, you must first draw a picture and draw a free body diagram. So here's our picture. Let's draw a free body diagram. Block A is where we're going to start. It has tension going up. I'm going to call the tension in this first string here, this one, T1. It has its weight going down, the weight of block A, which is mass times gravity. All right. Then we have block B here. It's going to have that same tension, T1, same string, same tension, but for it, it's going to be being pulled to the left. It's going to have its weight going down. It has a normal force going up. And since we said it's probably going to be moving to the left, that means that not only does it have tension 2 pointing to the right, but since it's moving to the left, friction opposes motion, it has a kinetic force of friction to the right as well. Boy howdy, this is getting pretty complex. Here we have block C. It too has a weight and a tension acting on it. And again, this tension here is T2, the same tension acting to the right on block B. So once you have your free body diagrams, you must also make sure to label the direction of acceleration. So we know that block A is probably going to accelerate down, which means block B will accelerate to the left, and block C will accelerate upward. So now you can do some of the forces on each block. Let's start with block A. There's no forces in the x direction, so that's easy. We can ignore that. In the y direction, we have T1 going up, we have the weight going down, and that equals ma. Wait, whoa, time out. What is this negative a business here? Well, it's accelerating in the downward direction, so we must put a negative in there because it's a negative acceleration. Also, while on the topic of acceleration, I want to make a quick side note. Do you notice all of these a's are the same? I did not put subscripts for each block. This is the acceleration of block A, but what I'm suggesting here is that it's the exact same acceleration as block B, the exact same acceleration as block C. How do I know that? Well, if we look over here, again, they're all tied together. So at whatever rate that block A is accelerating down, block B must accelerate at the exact same rate. If you don't believe me, take a string, tie it around your waist, tie it around your desk chair, and start running around and see whether or not you and your chair accelerate at the same rate. You will, trust me. So since they're tied together, they're going to accelerate at the same rate. So we have an equation here. We don't know T1 from our problem statement. We know m, and we don't know acceleration. One equation, two unknowns. Can't solve. Bummer. So we move on to block B. In the x direction, we have T1. I'm calling left positive since that's the direction it's accelerating. So we have T1 minus friction minus T2 equals MBA. Oh, again, we don't know T1 or T2 or A. We now have two equations, but we have three unknowns. Bummer. Let's look in the y direction. In the y direction, we have the weight going down and the normal force going up, and that is equal to 0. Again, you can call down or up positive. So just to make that point clear to you all, I went ahead and called down the positive direction here. Why is it equal to 0? Well, that's because block B is in equilibrium in the y direction. It's not flying up off the table or crashing through, so it's in equilibrium in the y direction. So we can see normal force is equal to mBg. That's a bonus. Makes us find what kinetic force of friction is more easily. But we still can't solve because we don't know T1, T2, or A. So we move on to block C, and for block C we have T2 going up minus mCg going down equals mCa, which is positive here because it's accelerating up. And now, boy howdy, we have 1, 2, 3 equations with 1, 2, 3 unknowns. You could use algebra to solve. But it would be pretty complicated. It would be quite a lot of work. So you can do it that way, no problem. Do some substitution and you're good to go. But you can also treat the system as a whole. So before solving it all the way, I want to show you how to treat the system as a whole. The great thing about treating the system as a whole is you can ignore all internal forces, forces acting internally to your different objects. So if we're defining our system as blocks A, B, and C tied together, this string 1 connecting block A to B, that's totally internal. T1 is resisting the motion here and adding to the motion here. They cancel out. T2 also internal. It's resisting the direction of motion here, contributing to the direction of motion here. It cancels out. So when you deal with the system as a whole, you only have to draw external forces. So the only external forces are weight of block A, weight of block B, weight of block C, friction on block B, and the normal force. That's it. And now what you can do then is, after defining the direction of acceleration the same way that we already did, you can do some of the forces for the system as a whole in the direction that it's accelerating. So this is where it gets confusing. If you're careful though, it's not too tricky. For block A, what is its direction of motion? Down. So you're going to call down positive for block A. What's the direction of motion for block B? To the left. It's accelerating to the left. So we're going to call that direction positive. Notice friction then must be negative. Block C is accelerating up. So we're going to call up positive when looking at block C. So weight C is going to be a negative force. So weight A is positive, friction is negative, and weight C is negative, and those are the only forces in the direction of motion. Normal and weight B over here are just equal and opposite. So when you set this up, what you have is a positive MAG minus the force of friction minus MCG equals MA for the system. Keep in mind, this M is the mass of the whole system. Mass A plus mass B plus mass C, the whole system. Okay, so cool, sounds good. From there, we should be able to solve. We need to substitute in what is force of kinetic friction. We're on a flat surface. It's just going to be mu multiplied by the normal force. And we already said normal force is going to be equal to just the weight of block B because it's a horizontally flat surface. If it was at an angle, it would be different. Keep that in mind. So we make that substitution, and then we can solve for our acceleration. Our acceleration is just going to be equal to all of this here divided by the mass of the system. I went ahead and factored out G to make it a little simpler. Again, the mass of the system is just MA plus MB plus MC. So if I plug in all my numbers, as you can see here, you can pause and double check with your numbers if you're not sure. But if you plug everything in, you should find that the acceleration is, boy howdy, a box-worthy 0.44 meters per second squared. Tricky problem for sure, but a really good one. So check it out. Let me know if you have any questions, and we're going to stop there for now at the end of Chapter 6, Section 1. Have a great day.